Hi, in this video, I would like to explain your FSM, which also stands for finite state machines. Again, this is going to be a two-part video. In the first part, I would like to explain FSMs in general and how FSMs are built, the types of FSMs. And in the next video, I will explain the FSM that's related to your Lab 5. So before you look at this video, I would advise you to look at the video posted by Dr. Kala, where he explains how to build a state machine, how to build the state table and state encoding. In this series, in this video, what I would like to explain is, assuming that you already have your state machine drawn and your state table, how do you translate that into Verilog? And I would like to compare the state machine to Verilog so that it becomes clear. Okay, so if you look at any state machine, right, a state machine is basically nothing but a sequential circuit. The general structure will be, you will have one combinational block followed by a bunch of flip-flops. Flip-flops, as you observe, is getting clocked, and then this followed by another combinational circuit. Now, this third combinational circuit that you see may or may not be needed. So more often than not, you don't need this combinational circuit at the end, but sometimes you need. So that's just for generalization. We have this combinational circuit. Okay. The important thing to keep in mind is that the combinational and the sequential circuits are all separate blocks. They're separate entities. They don't interact with each other. The only way they or maybe not that they don't interact with each other, they don't share signals. So the output from the combinational go to your flip-flop. So they're built independently. That's probably the better way to put it. And then finally, when you build a state machine, you put them together in hierarchy and you tie your signals. Another important thing to keep in mind is this feedback, that is going from your output of your flip-flop to the input of your combinational circuit. So most state machines that you will build will need to have this feedback, and I will again explain what this feedback basically means when I come to Verilog. But keep that in mind, this feedback is quite important. But generally, whenever someone tells that I'm going to build a state machine, the two things that need to come to your mind is that there's a separate combinational block and there's a separate sequential block or a flip-flop block. And once you have these two things in mind, building state machines will be very easy. Now, if you'll take a state machine, right, there are two most common varieties available. One is called the Moore state machine and the other is called the Mealy state machine. So first, let's look at our Moore type state machine. Again, if Moore and Mealy doesn't make sense to you, I would advise you to look at Dr. Kala's videos and then come back here. Assuming that you know what a Moore and Mealy state machine is, let me proceed. So a Moore machine, basically what it means is my output, as you can see here, output is Z. My output depends only on my current state or my present state. So when my state is A, my Z goes to 0. When my state is B, Z goes to 0. When my state is C, Z goes to 1. So as you can see, my output only depends on my current state. So this is an example of a Moore type state machine. Also, if this confuses you, you can also look at the state table. Again, these are all pictures that I've taken from your textbook, your Stephen Brown textbook for your digital design. And this, I believe, is chapter 6. So if something that I'm talking today confuses you, I would advise you to again go read your textbook as well. So if you look at the state table encoding, right, you look at your output only depends on your present state. Your next state or your, let's not worry about next state for now. And W is basically your input. So W is your input, Z is your output, and you have your ABC is your present state. So your output depends only on your present state and does not depend on your inputs. So that also gives you a clue that this is a Moore type state machine. Good. And then one thing that is very important when you're building state machines is this guy, reset. So from now on, anytime you build a state machine, you need to have a reset. Because once you hit reset, that tells your state machine where to start, which state to start with. If, for example, you didn't have this reset, right, and if you just had A, B, and C, then what will happen is when you power on your device, it might work in simulation, but when you power on your device, you don't know what state you're going to start with. So if you don't know what state you're going to start with, then you don't know if your design is going to work or not. So an analogy for this is, if you don't know if you're in park or neutral, or rather drive, you don't know if you're going to go forward or if you're going backward, right? So it's always very important to know which, if you're in drive or if you're in reverse. So something just like that. Okay, now the way to read a state machine or a state diagram is, let's start off with this state A. Upon reset, I come to state A. That's all it is. Upon reset, I come to state A. Now, when I'm in state A, if my input, which is W, is 0, then I go back and I remain at state A and I output my Z equals to 0. When I'm in state A, and if my W, which is my input, is 1, I transition to state B and then I output my Z equals to 0. When I'm in state B, let's say my input is 1, then I transition to state C where my output Z goes to 1. And then from C, if my input W is 0, I transition back to A where my output Z goes to 0. So this is a way of reading your state machine. Okay, so if the difference between Mealy and Moore state machine confuses you, right? The way I remember the difference is, I always remember more is less. More is less. So if you're in a Moore type state machine, the output depends only on your current state. Okay, now let's look at the Mealy type state machine. So this is another example from the textbook that I've picked up, and this is a Mealy type state machine. So the thing that you'll observe is, first you need to observe that there's a reset state. Very good. So when you're, let's say you're on state A, okay, when you're in state A, you will observe that when W is 0, my Z goes to 0. When W is 1, my Z goes to 0. So you see that the output, in this case again, which is Z, depends both on my present state and my present input, also called current state and current input. Again, if you look at state B, right, if you're in state B, and if my current input is 1, then my output goes to 1. But if I'm in state B and if my current input is 0, then my Z output goes to 0. So this is a Mealy type state machine. Again, in Mealy type state machine, the output depends both on my current state and my current input. Again, the table also will explain the same thing, right? My output Z depends both on my present state and my present input. So this is a very important difference between Mealy and Moore type state machines. In your lab 5, you can build your FSM as either a Mealy or a Moore type state machine. We will give you enough flexibility. So we want you to make that decision. Again, there is no it's not written in stone that you have to build a Mealy or a Moore type state machine. It's a design choice. So if you're comfortable with Moore type machine, build a Moore type machine. If you're comfortable with Mealy, build a Mealy type state machine. Okay, now let me quickly show you how you will code your Mealy or Moore type state machine. Okay, what is happening? Okay, good. So I have two files. Let's first look at my Moore type state machine. Okay, so in my Moore type state machine, what do I have? My input is W. I have a reset signal, a clock, and a Z, which is my output. And this is again for figure 6.3. Very important, guys, is your state machine needs to have a clock and reset along with your inputs and outputs. But never forget that you can never build a state machine without a clock and reset. Good. Then what do? I declare my inputs and outputs, right? Reset clock and W is my input. My output is Z. Good. Next, these two lines are very important. Okay. PS stands for present state. NS stands for next state. Okay. So every time you look at a state machine, right? Let's say you're in A, then your present state is A, and let's say input W is 1. Then your next state is B. Once you go to B, your present state is now B, and if your input is 0, your next state goes to A. So whenever you want to transition in a state machine, right, you need to have something called as a present state and your destination as your next state. So in your textbook, what they have is this is a lowercase y and uppercase y, which I think is really confusing. So I would much prefer doing PS and NS because more human readable. So PS is my present state and NS is my next state. Now, you might be wondering, why is it 2 bits long? Well, the reason quite simply is because I have 3 states, right? If I have 3 states, I need 2 bits to encode each of these states. So let's say A is 0, 0, B is 0, 1, C is 1, 0, right? So that's why I have 2 bits. And now this keyword called parameter, right? Parameter, basically what it does in Verilog is it allows us to set a binary or a bit value to an alphabet or a word. Okay, in this case, what I'm doing is I'm declaring a parameter which is 2 bits long, and the parameter A is encoded as 2-bit binary 00, B is 01, and C is 10. So basically at this point what I'm doing is I'm encoding each of these states with a appropriate binary value. The benefit for this is now, because I can directly say A goes to B or B goes to C, rather than saying 00 goes to 01 or 01 goes to 10. So it's more easy to debug if things go wrong. Okay, now you see that I have two always blocks, and one always block is my sequential and the other is my combinational. So again, if you remember from the first picture that I showed you, right, you have your combinational and your sequential as two separate entities, and then they tie together. So that's basically what you're doing right here. So in your sequential block, so your sequential block in any state machine you build, right, it's only going to be these two lines, more or less, right? So the first thing you want to do is you always want to do negate of reset. Why negate reset is because my reset goes to push button, and then pause of clock. If my reset is 0, right, then my present state is A. Again, keep in mind that you have to use non-blocking. Why non-blocking? Because you're using pause or negate and there's a clock. Again, this is a rule of thumb which I've explained to everybody. Okay, so the way you read this is when I'm reset, then my present state is A. So that's, you see this transition, when reset, my present state goes to A. So that is basically what you're encoding right here. Else basically means if I'm not resetting, then on every positive edge of the clock, my present state is my next state. So what this means is, this is also again very important, guys. If you look at a state machine, right, it transitions from one state to another state, or it can remain in its own state, but this happens every clock cycle. So every clock cycle, so if I'm at A, on every clock cycle, either I go back to A or I go to B. And if I'm at B, every clock cycle, I go to C or I go to A, right? So that's the working of a state machine. So what this line tells is that on every passage of clock, my present state is whatever my previous next state was. So in this case, so let's say I'm currently at A, and let's say W is 1, right? Then my present state is now B, right? Which previously was, B was previously my next state, which is now my new present state. So that's what this means. Okay, if this confuses you, please think a little about it and it will completely make sense. Finally, what we do is we have our combinational block, right? Combinational block, again, the textbook probably tells you to put all your combinational signals in here. I just prefer putting the star, because then the tool will, it'll do it'll pull whatever signal it needs right here. You don't have to worry about it. Okay. Next, I have a case statement. Again, all your state machines, right? Guys, don't build your state machines with an if-else statement. Okay. Always build your state machines using a case statement. Okay. So my case statement, the case condition is my present state. So always at my present state, if my present state is A, right, which is what I'm starting at because I have currently reset my system. If my present state is A, then if W is 1, my next state goes to B. See that? That is basically what's happening right here. At A, if W equals to 1, my next state equals to B. Else, my next state is A. Else basically means W equals to 0, my next state is A. Right? So my next state is my output, right? So the combinational block, if you observe this, right, it worries about setting my next state, and my sequential block worries about setting my present state to my next state. So this is the feedback that I was talking about, right? If you remember from the general structure, there is this feedback, right? So that is what this is. So the flip-flop, it gives me my present state, which goes to my combinational circuit, which will generate my next state, and then so on and so forth. So that is basically the feedback that we have implemented over here. Again, basically, if W equals to 1, goes to C, else goes to A, and blah, blah, blah. The important thing is you always want to have a default statement in your case statement. Even if you've covered all the cases, does not matter. Always have a default statement. And in my default statement, what I would like to do is I set my next state to X. X basically means it won't set it to A, B, or C. The reason I want to set this to X is because when I'm testing this in model sim, right? If I see X's, then I know that my state machine is not encoded, or I'm not described my Verilog for state machine correctly. Also, the other reason is that when you're building very important systems, right? Let's say you're building a missile control, or you're building an airplane controller, right? You can't just randomly say next state equals to A, because what will happen is instead of your plane going up, it'll go down. So my professor would always say that all these small errors is the reason planes crash. So strong example, but it's used to drive the point home. Good. So finally, you also need to worry about your output Z, right? So in this case, you see you have your combinational, sequential, and another combinational block. Again, so this is this general structure. If you look at it, combinational, sequential, and combinational. So if you observe from the truth table, my output Z is 1 only when my present state is C. Other times it is 0. So that is how this is encoded, right? If my present state equals to C, then this bracket will evaluate to true, which means my Z is going to be set to 1. Other times when present state is not equal to C, this will get evaluated to false, and so Z will be set to 0. If this line doesn't make sense, you can also write it as this way, right? Always at start, if present state is C, then my output Z goes to 1, else Z goes to 0. So this, you can either do it this way or this way. So this is more high level way of describing it, but if you can also do it this way, no harm. Good. So this basically is how you will define or declare a Moore type state machine. So as long as you follow this template, right, you have a sequential block and combinational block, things should work fine. You will not get something called an inferred latch. Okay, so most of you, if you miss any of these steps, right? So for example, if else, if there's an if, you also want to end it with an else. If else, if else. If you just put if and then you forgot an else, for example, right, you will end up getting an inferred latch. The problem with an inferred latch is, if you all remember from the previous labs, right, that it will sometimes make your behavior not work the way it is, right? Inferred latches are very wrong. Good. Now let's look at the examples for a melee type state machine, right? Again, if you remember, reset and clock, very important. Input is W, output is Z, right? Output reg. The reason my Z, which is output, is of type reg is because I will set that value inside my always block. So it's Verilog always wants it to be of type reg. Again, if you observe the melee type state machine, right, there are only two states, A and B. So I can encode A as 1 and B as 0, right? Or the other way around. I can say A equals to 0 and B equals to 1. So it's a 1 bit. And then that's why I have 1 bit present state and 1 bit next state. Again, this is also very important, guys. If your state encoding is 2 bits long, then your present state and next state also should be 2 bits long. Okay. Again, sequential block, no change. Negative reset, positive clock. If reset goes to 0, present state is A, else present state is next state. Perfect. All of you know how this works. Now, at combinational block, right? Again, based on my present state, if A, right? Let's look at the diagram. If W equals to 1, Z goes to 0, and my next state is B. See that? If W equals to 1, Z goes to 0, and next state equals to B. Else basically means if W equals to 0, right? If W equals to 0, Z goes to 0, next state remains at A. So Z goes to 0, next state remains at A. And the same with B. And again, default, I will set them to X and X. And done. You now have a way to write both melee and Moore type state machines in Verilog, and I also have translated it to my state machine. So this should make complete sense to you guys. Good luck.